The near corner, we have Michael Shapira of Hebrew University. And Keith, where's Keith?
Come on in.
Keith's right there. And soon we will have a contender in the far corner. But first we need the laptop to work.
This work?
There we go.
Yeah.
Okay.
Like that. Okay, hi everyone. So this is based on a true story. Not too long ago, Keith and I were seated next to each other on a flight. And naturally, at some point, the discussion turned to congestion control. And because Keith and I rarely agree on anything, this was the outcome. And this is the story of that debate. So the good news is that since then, Keith has accepted the superiority of my claims and fully agrees with everything I'm about to say.
It's not true. It's not true.
It is true.
It's not true.
It is true. Okay, there's no need to convince anyone that congestion control is an important topic. There's many papers about this. It's hotnets. What I want to do next, though, is talk about three recent approaches to this challenge that are very different from each other. The first is REMI. So REMI basically takes as input a global optimization goal and assumptions about the network. And then what it does is it generates a model of the network, and it seeks offline a protocol that optimizes this global objective within the generated model. BBR is a different approach, which models the network pipe as a single link and effectively tries to track the bottleneck bandwidth. And then last, we have PCC, yet another different approach, which associates each sending rate with the resulting performance expressed in terms of a utility function and tries to empirically map history to a good next choice of rate. And the way I see it, there's two fundamental distinctions between the different design philosophies underlying these three approaches. The first is white box versus black box. So both REMI and BBR are white box approaches in the sense that they generate a model of the network, whether offline in REMI or online in BBR, and then they use this model to guide rate selection. PCC, in contrast, is a black box approach in the sense that it doesn't assume anything about the network or try to infer anything about the inner workings of the network in real time. What it does instead is it inputs into the network sending rates, it observes the resulting performance, and it uses this feedback loop to guide rate selection. Another key distinction is local versus global optimization. So both BBR and PCC try to optimize a locally perceived notion of performance. In BBR's case, it's fully optimize the network bandwidth. In PCC's case, it's optimize some local notion of a utility function. Right? REMI is different. REMI builds into the protocol behavior that's supposed to optimize a global objective, say proportional fairness. And my personal take is that with the exception of highly controlled specific environments, there's two hard truths that we must come to terms with. The first is that you can't accurately model the network. Right? There's too many unknowns. So flows come and go. Different flows might utilize different protocols. Different routers might utilize different queuing policies. We may have physical layer corruption. We may have middle boxes. We may have packet processing in software. We may have stochastic losses, et cetera, et cetera. The second hard truth is that you cannot globally optimize at global scale. So firstly, there's no agreed upon notion of what it is you would want to optimize. Right? Does it make sense for the internet to be proportionally fair? I'm not sure. Like, why would you have that? But regardless, even if you did have such an objective function, given everything I've just said, why would you think it's feasible to actually attain it? And this leads me to concluding that instead of relying on an inaccurate network model, you should utilize a black box approach. And instead of aiming for a potentially infeasible global optimum, you should focus on realistic goals. And by realistic goals, clearly I mean optimize local performance, but also global goals like fairness on bottleneck links, like quick utilization of spare capacity, like quickly converging to equilibrium points, et cetera, et cetera. And in terms of what this means, I think that what this means is moving away from the traditional schemes for generating congestion control protocols like network utility maximization, which is very useful in certain contexts, again, highly controlled environments, but I think is not necessarily well suited to the wild. And one approach that we're currently investigating is applying online learning. So online learning is, there's a rich body of literature in machine learning and non-cooperative game theory on online learning. In a nutshell, it's a very powerful abstraction for reasoning about uncertainty. So specifically, you have a decision maker. He repeatedly makes actions. In our case, he repeatedly selects actions. In our case, actions translate to rates. And the consequence of each action is only known to the decision maker after the fact. And the remarkable thing about online learning is that we have algorithms with provable guarantees, both from the local connections perspective. This is termed no regret in the literature, but both from the local connections perspective, but also from a global perspective, like, say, quick convergence to equilibria. So we started working on this a few years ago with Bryden and the rest of the folks at UIUC. And one thing I want to emphasize is that PCC, which was proposed in 2015, is both a paradigm and a specific realization of that paradigm. And I think that the paradigm is very promising, but I think that the specific realization is far from fully tapping the potential of online learning. And this is one thing we're working on now. We have some promising results. And I guess we're done here. Thank you very much.
Whoa, hang on. I have something to say. Can you bring up my slides?
Sorry.
No, do you have a PDF file on your hard drive?
There's no time.
I
wish I could. I wish I could.
There's a PDF file on your hard drive. Can you just,
Brighton,
can you please?
It's been 15 minutes.
Open it.
OK.
We have a few more minutes.
Sorry. This is not intentional, but it might take me 10 minutes to fix, though. So.
All right, I brought my own clicker. It's all right. It's all right. Can we full screen? Is that possible? Can I just have a postage stamp of your screen?
I think we can.
All right. How about in the window menu and then the view menu? Sorry.
View menu.
Should never have agreed to do this on your laptop.
Honestly, I'm not doing this on purpose.
Command L.
Aha.
All right.
Go ahead.
All right. So, my colleague tells a very seductive story. He's been doing it his whole career, but I think it's important that we recognize some ground truths here. There's some statements that Hamilton makes that sound appealing, that make you want to file him, but they have to be read extremely carefully. This man is a master. They have to be read extremely carefully to be understood in context. Let's look at some of these statements. PCC makes no assumptions about the underlying network conditions. Instead, observing which actions empirically produce higher utility and therefore achieving consistent high performance. Let's see what that means. Number two, online learning algorithms. We're told this is the new paradigm. There's global proofs and all kinds of exciting things. Let's see what we really get out of online learning algorithms. Provable guarantees even under the complete uncertainty about the environment. All right.
All true statements.
Here's Burr's position. Michael, Hamilton. Every scheme embodies preconceptions about the network. Whether you want to talk about them or not, whether you write them down or not, whether they're explicit or implicit, every scheme embodies preconceptions about the network. PCC is not necessarily bad, but this idea that it's a new paradigm, that it's totally different from everything else. And number two, online optimization. When you're online, a flow can only observe the fate of its own traffic. You can only see what happens to your packets. And if every flow greedily optimizes the utility function as a function only of its own traffic, the result is badness, at least over a normal kind of network. I don't think you can escape this. All right, let's talk about this in turn. Number one, PCC makes no assumptions about the underlying network conditions. That's just not true. How can you write this? How can you write this in all of your papers? These assumptions, maybe you don't write them down, maybe you don't admit that you have them, but I bet in the shower you probably think maybe Burr is right, maybe I have them, because these assumptions are everywhere. Whether you state them or not, they're in all your constants, the initial window and the min RTO, and then what you do on the window increase and decrease, and what the penalty is for loss. And the inputs, what do you care about? Is it duplicate acts? Is it timeouts? Is it delays? Is it explicit congestion notification? You're making assumptions about the network and the behavior. The world is ambiguous. You don't know what's happening. You get some acts. You don't know if that means that the link is slow, or the link is lossy, or the link has competition. You don't know. The situation is ambiguous, and what you do indicates assumptions. As with every other scheme, PCC's got constants and behavior that embody assumptions. Like you assume the loss rate is less than 5%. That's an assumption. As with every other scheme, PCC performance depends on how close the real network matches those assumptions. Let's look at some data. So at Stanford, we have this congestion-control data archive. We take data every week. Here's some data that was collected yesterday, not just automatically collected. Here's a test from over the kind of network that PCC was probably designed for. This is a shallow buffered wired network. The performance is freaking awesome. It's fantastic. Everyone, TCU seems to be cubic, like 500 megabits per second. PCC gets like 900 megabits per second with no added delay. That's fantastic. That's where your assumptions match the network. Here's a deeper buffered wired network. This is a wired network in Brazil. So here you're getting marginally better throughput than TCP cubic, but at the cost of a lot more delay, like more than 4x more delay. It's not so great. I mean, it's good. It's not great. All right, here's a wireless network, a cellular uplink in Bogota, Colombia. Here you're getting 32 seconds of delay. And this is your latency-sensitive scheme. 32 seconds of delay with no more throughput. That's not so good. At least you get the same throughput. Here's a cellular downlink in New Delhi, India. Here it just sucks.
Don't make this personal.
It's about the scheme, Hamilton. All right. So this idea that you get consistent high, like how can you write this? First of all, consistent high performance, just empirically not true, but therefore, as if there was some theory of congestion control that could produce an implication that you get consistent high performance, this is fallacious. It's not true, and it's definitely not a therefore. I mean, we just have to measure it and see. We definitely don't have the science yet to be able to say therefore. Number two, online learning algorithms. All right, the problem here, I know it sounds good, like why do you have to learn offline? Let's just learn online. It's very seductive, but when you're optimizing online, you can only see what happens to your own traffic. And if each flow independently, greedily optimizes some function of its own traffic, the result is probably badness, unless the network provides some sort of assistance like separate queues or basically separate queues. Or some sort of feedback that occurs before you overflow a buffer, like a red type scheme. So PCC, first of all, you talk about a utility function. It doesn't have a utility function, because you had to do this very careful utility engineering to even get it to work. If every scheme just optimized its throughput or some function of its throughput, it would totally not work, because every scheme would just send as much as possible. So you don't do that. Instead, you have this artificial loss penalty where you say, even if the throughput is great, we're still going to penalize loss. This is just like TCP AIMD. Just like a loss penalty. Van Jacobson designed it into TCP. You've got this penalty you've designed in your function. And it only works with this penalty. If you say, we're just going to optimize throughput or log throughput or something like that, it totally doesn't work. And here's that red term. Beyond like a loss of like 7%, you get like negative utility. That's an assumption. It's not maybe a bad assumption, but it's definitely an assumption. If you run over a stochastic link with big loss, it doesn't work. So I did some theoretical numerical experiments to look at the consequences of this, of everyone optimizing separately. This is a very classical case here. It's a two-hop parking lot topology. We got one flow that crosses this link, one flow that crosses this link, and one flow that crosses both links. And the question is, if you start up flows in an arbitrary order, you look at what throughputs, what rates do they eventually arrive at. So the good news is PCC does always converge. But the bad news is that it converges on crazy outcomes that depend on the initial conditions. It depends on the order in which the flows start. So this is looking at the throughput of flow C, the one that crosses both links. Depending on the initial conditions, you can either get 2 megabits per second, or you can get 6 megabits per second. There's a 3x slop that depends on the order that the flows start in. And then you end up with a throughput that goes forever and ever 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 and ever. Forever. Because every flow is independently trying to optimize this function, and you get stuck in a situation where no flow has reason to increase. This is not a problem of regret. You keep talking about no regret, but no flow has regret here. They're all sending at the optimal rate for them, but depending on the order that they started up in, they end up with very different rates. Now, what happens if we don't try and design an objective function to maximize? What if we just design an algorithm? And whether it's me designing the algorithm or a computer program designing the algorithm doesn't really matter. We design an algorithm, very dumb algorithm here like AIMD, you get the blue dot. Algorithms can converge. Algorithms can get good performance. But objective functions that everyone independently, greedily optimizes, I don't believe it. So this is the theoretical result. This is not about the PCC implementation. This is just about the math. But we can look at it in theory, too. This is, again, from the Stanford Congestion Control Data Archive. This result was, again, taken yesterday. We look at 3 flows starting 10 seconds apart. Here's TCP cubic. So the first flow and then the second flow comes in. It's not perfect, but it kind of matches it. And then 3 flows, they kind of share. TCP cubic, it's not so bad. Let's look at TCP BBR. Here's the first flow. Here's 2 flows. Here's 3 flows. It's actually not so great, but it's trying. And now it's PCC. Here's PCC. It totally doesn't work at all. The first flow just starts and it's just totally oblivious. Then the second flow starts, let's try a high rate. We're totally oblivious too. And the third flow is like, well, I'll try a low rate. It's exactly the result that is predicted by this theoretical result here, where the order of the starting flows can end at totally arbitrary outcomes that then last forever. That's the outcome. So look, designing a congestion control algorithm is feasible. Designing a congestion control objective function and then having every node online optimize it separately, I doubt it can yield good results, at least over a network with shared drop-tail queues. And in the paper, I have a conjecture in more formal terms that says this is impossible. PCC demonstrates this effect in theory, in measurements in emulation, in measurements over real paths that were taken yesterday. So look, this problem, we shouldn't call it congestion control. That's like a branding problem. We should call it resource allocation. This is one of the fundamental core problems in networking. There's security, which is who can do what, and then there's resource allocation, which is if you can do it, how much of it do you get? Those are the only 2 problems in networking: security, congestion control. So we should just call it resource allocation. It's a core problem in networking, and there's so much, even after 30 years, that we still don't know. I bet this talk, this session here, we're going to get like the worst of time award. Because in 10 years, people will be like, what were those guys talking about? They had no idea what they were talking about. I hope so. I hope the field advances enough in 10 years that we will get the worst of time award. This remains a fascinating area, and there's so much still to learn. Because you can look at the results. It's so terrible today. So that proves there's so much still to learn. Online learning, I don't believe it's a silver bullet. I think independent greedy optimization can lead to badness. Whether you have no regret or not, I don't think regret is relevant. This doesn't mean that PCC or its future no regret progeny are bad. But it does mean they're not in a different category. This paradigmic model with this white box and black box and whatever, that's the red herring. These schemes are not categorically different from other schemes. They have to be evaluated on the same basis.
My turn.
Boom.
OK.
Drop clicker.
OK, so I hope you didn't fall victim to this explanation. So, 3 different responses.
Oh, I haven't seen this.
Aha!
Oh.
You actually have seen this.
All right.
OK, the first thing is actually, I think, the simplest response, right? TCP has had 3 decades to evolve. PCC has had 2 years. Within these 2 years, we've done quite a bit of work, right? And I believe that a lot of what you show is just an artifact of the specific implementation of PCC, right? And we actually are playing with different approaches, right? And with advanced models. And in fact, PCC doesn't even give you the, and by PCC I mean the specific formulation of PCC we had before, the specific implementation, the most basic requirements one would expect from an online learning algorithm when tackled from a formal perspective, right? So this is one thing. But more importantly, right? White box versus black box is really important, and let me tell you why. Right? Here's an analog. Right? Computer vision. You want to identify cats in pictures. Right? There's a white box approach. The white box approach is think really hard about what's a cat. Right? What's the shape of its ears? What's the shape of its teeth? And then look for cats in pictures. Now, empirically, this is a bad approach. Right? It hasn't proven useful in general. Right? What has proven useful? A black box approach, in this case, a machine learning approach. Learn good mappings from input pictures to labels, right? And then figure out what's the right answer for the next input picture. Right now, Keith would argue, and this is the analog of Keith's argument, that any machine learning model, say a neural network, carries assumption about what's a cat, right? But it doesn't, right? In fact, one of the biggest questions in machine learning these days is explainability. The state-of-the-art machine learning schemes are not explainable in the sense that you can't reverse engineer what a cat is from a neural network that does a good job at this task, right? And this is the same for PCC, right? You can't
It's
necessarily...
unexplainable?
I'm sorry?
It's the same for BC, it's unexplainable? Or what was the point?
No, it has provable guarantees. This is not voodoo, but yes, it's unexplainable in the sense that you'll get performance guarantees, but you won't eventually say, hey, this was because I experienced 2% random loss, or hey, this is because I exactly matched the bottleneck bandwidth, right? In that sense, it's, I think, the same thing. And going back to Keith's argument, this is not about finding an approach, a black box approach, that's optimal in all possible contexts. Again, think of machine learning. People work really hard on optimizing the machine learning model, right? Do I have 3 or 4 layers in my neural network? How do I represent the input, et cetera, et cetera? This does not make them white box approaches.
Can you label, though? Everybody knows what a cloud looks like.
What, I'm sorry?
Everybody knows what a cloud attack looks like. And there is a very heavy exercise in labeling.
Yeah.
Can we label network states as good or bad?
So I think
Who would
that's where-
label?
That's a good question. I think the analogy fails there, right? When I talk about labeling, I'm not talking about this specific task, right? That's a labeling task. I think in the network context, we're actually in a different world of machine learning, specifically reinforcement learning. So I think that's a completely different area, but I think that this argument applies, right? And the last thing is, I don't want to linger too long on Burr's conjecture, because I think regardless of whether it's true or false, it doesn't matter because you can't optimize a global objective, so you're stuck with optimizing local objectives. But I do conjecture that it's false. And the reason I conjecture it's false is precisely because of network utility maximization. So network utility maximization tells us that TCP Reno, for example, can be viewed as optimizing a local goal for the specific choice of utility function, I think arctangents or something, right, in drop-tail networks. And you do converge, right, to a globally optimal social welfare maximizing goal. What's the problem? The problem is that under network utility maximization, for this to work, you have to assume that flows are elastic, that you have network support and everyone is using drop-tail, that everyone is optimizing this local perception of a utility function like arctangents, et cetera, right? This is where these approaches fail, I think. They talk about what happens eventually under very strong assumptions about the network. I'm done.
That's your student's clicker.
Yeah, and actually this is yours, right?
No, this one is mine. I borrowed that from Asaf.
Can I drop yours as well?
Should we take questions?
Or a vote?
You want Nancy? I mean, look, Michael, the result you're alluding to is that, we're not alluding to, the result you're mentioning is that if you design an algorithm that has a particular behavior at the endpoints, like TCP Reno, like it increases by 1, and then if it detects a triple dupeac, it divides by 2. That's a particular algorithm, and if you run that algorithm globally over drop-tail queues, you get over the long term.
Don't try to create a distraction.
You can prove that you get a particular outcome. But TCP Reno is not a PCC type scheme. It does not online optimize a utility function.
You had a conjecture. Your conjecture was that you can't locally
bring up
optimize.
Bring up the conjecture.
Wait.
It's my okay, here we go. Okay, look. Here's the precise conjecture. It is impossible for a decentralized congestion control scheme, one that greedily optimizes an objective function whose only input is the fate of its own traffic, to be globally asymptotically stable over a network with shared drop-tail queues. That's a conjecture.
This is exactly what happens in now.
Reno doesn't optimize an objective function. It does a particular thing. It's an algorithm.
Teaches us that it does, right?
No, not a locally observable objective function. Reno is an algorithm that, if everybody runs it, produces a global outcome. There is no number in Reno that represents the utility of a particular sender.
No. Actually, there's precisely that.
If we want to have time for questions, we should.
Okay. Or I thought we have till 10:45. That's what it says on the program. It says coffee and throwdown break. Michael, I think you're getting feedback on the podium microphone. If you come closer to me so I can shoot you, then all right, great.
Yeah.
Okay, a few questions.
Hi, I'm Matthias from Columbia University. I'm actually curious how you define your no-regret algorithms and what the setting you place yourself in, and more precisely, whether it's like bandit regret or pure reinforcement learning. Because like there's a pretty major difference where in bandit you would have no regret compared to realized outcomes. and that it seems like since you influence the future outcomes, it can basically lead to pretty bad things. Maybe that's what we're saying.
So I think you're right. So what we've investigated so far is the bandit setting, right? Where, as you say, when I test a specific rate, I don't know what outcomes other rates would have generated, right? I only know what I actually experienced. And in that sense, it's a multi-armed bandit setting, right? But more broadly, right, this is a very degenerate case of reinforcement learning, right? And there's, the sky's the limit in terms of things you can look at.
I think Vias had his hand up next.
Phil Levis, Stanford University. So actually, you claim that these results from, say, deep neural networks are not explainable.
Sorry?
You claim that the results from deep neural networks are not explainable?
Necessarily, right?
Why not? It's a function in a high-dimensional space, right? Adversarial machine learning, right, demonstrates like you can absolutely produce, counterexamples, et cetera. I'm not sure that's fundamentally true. Just because people aren't trying to, they're using like black boxes. They want to twist out some Python, but. So, I mean, you made a claim about whether these things are explainable at all. I'm not sure that's correct.
So I think.
Can you sort of unpack that?
So let me try, right? That's a good question, but let me try because I think that there's a distinction between two things, right? One is things like GANs, right, where you can create a counterexample, and I think that's a fascinating research direction, right? I give you a protocol, and I ask you where does it fail, right? I think that's a good, and it does something in terms of explainability, right? But when I say explainable, and I think that's the standard term, what that means is that I can generate a model that explains, right, why the outcome is such and such, right? That is, if you were to look at this computer vision example, right, explainability in this case wouldn't translate to give me a set of instances where you didn't recognize that it was a cat. I think it would translate to, can you generate a model of a cat from this neural network that I gave you?
So, I think it's a great discussion. And I think this discussion is reflected in people's thought for quite a bit, as you probably know, in the context of reinforcement learning. There are two classes of solution, model-based and model-free, right? Now, model-based...
Keith wouldn't agree with you.
Right, obviously. Yeah. So model-based is basically you have faster convergence, it's more sample efficient, but introduces a model basis. The model basis is the difference between the model you have and the reality. The model-free methods takes longer to converge, but converge to better solutions. At least in that kind of community, it's kind of the trade-off, right? And I think that you see a little bit here, but maybe it will be good to frame also in this context.
Vias has had his hand up for a long time.
I'm actually going to ask a question, and maybe both of you can disagree with me. I'm actually not sure no regret is actually a very useful guarantee in practice.
I agree.
No regret is actually not a very useful guarantee
in practice.
I agree. It's a very weak guarantee. It's a nice theoretical abstraction, but it's actually a very weak guarantee in practice. The other thing actually maybe for both of you is, right, I mean, if you talk to our theoretical colleagues, the online optimization community does a couple of different things. One is regret guarantees under an adversarial model. They also look at like stochastic optimization problems where you can make like stochastic assumptions about like, hey, look, the world is under 5 probability states. And you can actually do a stochastic optimization as opposed to an adversarial scenario. And that's where the difference between like sort of model and model-free approaches start to blur. And I actually think that might actually be more relevant to make progress in this space than sort of a purely adversarial point of view.
So also I want to make a point actually, there are solutions which are using both. They're using model-based to get to a good starting solution, to a good state, and then model-free to further optimize to get to a better solution.
Yeah, but so I don't think you could optimize a self-driving car that only cares about its own fate. You have to care about the other cars.
So just maybe one...
Yeah, that's multi-agent. I mean,
just one short response to both Vias and Jan is that I agree, right? That is, once you accept a distinction between model-free and model-based, right? There's a lot of research questions one could ask. And the thing about adversarial models is that you have provable guarantees, right? Often it might be that empirically you want to transition beyond that. It might be that you want to train using a model to get the initial starting point. I think that these are fascinating directions.
We're quite a bit over time, but really quick, I see two hands up for a while. So Hari and then Van.
Just a quick comment. In India, you do optimize driving by only worrying about yourself.
Sorry, what did you say?
I was just, in India, you optimize driving only by worrying about yourself. So in some parts of the world, it might work. But so I think that, so I have a bias here with respect to believing that true artificial intelligence will arise only when you actually are quite a bit model-based. So, and I think that kind of treating everything as a complete black box leaves a lot of opportunity on the table. That I think that, this cat example, and I've seen such examples before, it really drives me nuts because human beings learn, toddlers learn about cats after like looking at 3 cats, and they're able to generalize that, and I think it's because they learn about models. I think they learn to interact with the world because they build up models of the world that are predictive. And actually recently, Jan LeCun has been out giving these talks about how he believes that it's really important to have models, predictive models of the world in which to optimize AI systems. So I think that you sort of by characterizing this work as a complete black box really leaves a lot from where I think the research could be going.
I don't know how to follow that. That's a great comment. Come down on Keith's side and agree with almost everything he said except his conjecture about optimization, which is the whole point of a network is you're sharing resources and different flows are coupled by the sharing, and the sharing gives them their visibility of their impact on the global action of the network. This was formalized by Norton in something like 1981, where this is one of 2 big mistakes in Michael's slides about BBR. So Norton showed that any multi-hop queuing system can be reduced to a single path that's state dependent. And so from the point of view of an endpoint, looking at just a single path but a time varying bottleneck, you're looking at the Norton equivalent queue of the multi-hop path. And so you're not losing any information. You're still modeling everything that you can see. Ellen Hahn, in 1978, working with Bob Gallagher, gave the original basis for network fairness, min-max fairness, to handle sources that don't always want to send and are sending over different links. And the starting point for her proof of min-max optimality and achievability was when you're at the min-max operating point, every flow is getting its bottleneck rate. That generalizes because its bottleneck may be the application data generating rate. That's the result that Klenrock and Gale used in '86 to show that if every flow operates at the max power point, then the network is operating both fairly and as efficiently. There's the maximum delivery and the minimum head-of-line blocking, which is why BBR is working to operate at the max power point. As Keith's graphs show, it's nowhere near successful, but we're trying to achieve that theoretical optimum. It's idealized, but it's all we've got. This is a theoretical optimum that's measurable from a single point in the network by measuring its activity, because you're coupled through the queues, which tell you in the delay.